Hello, lovely viewers. I am back again with a physics talk that I held actually 2 days ago. Um, but I recorded one of my training sessions the day before. So I figured I'll upload it here. Now, first, a bit of an introduction. So, this was for well, it's technically the second EIC UK workshop, but it's practically the first. We'll get back to that. So the EIC is the electron-ion collider, which is what I'm working on with my PhD. I'm doing both sensors and simulations of a full detector. This talk is on just the full silicon vertex tracker, so it's the innermost detector of the thing. Now, the EIC will be built in the US over the next sort of 10 years, and it's sort of the next big thing in the particle nuclear physics interface. So, well, in practice, I'm looking at sort of the inside of the proton. So I'm looking at the charm quark content in the proton in practice, and I'm developing a detector to help us in this endeavor. And that's basically what this talk is about. It's about my simulations of this innermost detector and how that's going, and some results from using actual physics events. So this workshop is for the UK and the EIC effort in the UK, which is sort of just taking off, which is why I'd sort of call this the first proper workshop. There was one a few years ago just to gauge interest, but now we're actually getting started in the UK. So the University of Birmingham, I would say, is leading this effort. We've done the most work so far anyway. And now we're asking for some big money from both the US and the UK to get this going. Anyway, this workshop was to gauge the overall UK interest and to present what we've done in different areas already, and this talk is part of that. So the talk before was by my supervisor, and it was about the sensor technology mainly. So that's why you'll see in my talk there are some links to the previous talk. I'll put a link to the whole thing in the description so you can look at the slides if you want, and so on. And yeah, that's about it. So enjoy this physics talk, I suppose. Hello, I'm Håkan Menlev, and I'm from the University of Birmingham, and I'm going to talk about some simulation studies of a silicon vertex tracker for EXT experiments that we have done here. This is an outline of the talk, so I'll start with an introduction containing the motivation for this work, the simulation tools used, and a basic geometry description, because the basic geometry is always the same, but then we alter the parts of it. This work is sort of done in two parts. The first is baseline layout simulations, and then we have physics performance simulations, which is sort of just getting started. And then I'll talk about future work and some conclusions of this work. Now, in this image, you can see full detector with an EP collision event in, and then this red box zooms in on the part I'm working on, which is the silicon vertex tracker and the general tracking area. So, the motivation for this work is, well, we're building on from the technology studies, so we're sort of taking the chips into the full detector. So this was discussed in the last talk by Laura. Now, we use simulations because it makes it easy to see the performance impact of changing things like pixel size, material budget from the sensors, the magnetic field, and so on. And the goal of all this is to develop and test a silicon vertex tracker and take the technologies into account. So to do this, we're investigating different silicon vertex tracker concepts and optimizing the layout and the parameters. And also, our goal is, of course, to understand the constraints that this detector puts on the physics measurements we want to do. And as I mentioned before, two types of simulations are run: the baseline ones with single particles, and then the physics performance one using generated collision events. So they're more specific, so to speak. Now, the tools used for this are listed here. So first of all, we have EIC route for the basic single particle simulations. Now, this was developed at Brookhaven based on a framework built for the FAIR Lab, and specifically the Panda experiment. It's geont-based and has single particle gun input. Now, for more advanced, so to speak, physics events, we use Pythia 8 to generate these events. We have some in-house expertise here with Phil Ilton. Then these events we put into a framework called Fun for All, which is used and developed for the S-Phoenix simulations. And this can propagate and reconstruct physics events. Now, since this is used in S-Phoenix, it's a well-vetted simulation framework, which is nice. It's also geont-based and has event-generated input. Now these simulations take a while to run, so to help mitigate this, we're using the University of Birmingham Blue Bear High Performance Computing Service, which is very handy. Now onto a basic geometry description. So here we see, well, layout cross sections. We have silicon and gas TPC concept here, and an all silicon concept here. So we call this a hybrid, and this all silicon. Now they have, of course, things in common. First of all, we have a beam pipe running through the center of the detector, and then outside it we have barrel layers, silicon barrel layers, which are concentric around the beam pipe. Then in the forward and backward regions we have the silicon disks, and then outside of the silicon barrel we have either a time projection chamber like here, or more silicon layers like here, and larger disks in this case as well. So this is the basic layout. Now, the baseline performance simulations are done in EIC route, as I mentioned. They're carried out for both silicon plus TPC hybrids and all silicon tracker designs. And these studies have covered, well, they've been going on for 2 years or so, so I can't possibly fit it all into this presentation, but I will pick out a few important examples. So they covered the central and the forward and the backward regions, and also the interface region between the barrel and the disks, and also silicon plus TPC hybrids compared to all silicon layouts. The figures of merit for these studies are relative momentum resolution and transverse and longitudinal pointing resolutions, which is basically the vertex resolutions. So as I mentioned, only highlights will be covered in this talk, but we've written a report of all the results in the EIC route up to February. And this is the table of contents for that report, and can be found at this link as well, and I've also uploaded it again to this meeting. So let's go through this a little bit. So first of all, some baseline design parameters are listed on this slide. So we start with modified beast concept, which Laura mentioned as well, which is based on the Alice ITS-2. We have two, so this is a cross-section along the beam direction, a sketch. We have 2 inner barrel layers and 3 outer barrel layers, and 7 disks in the forward and backwards regions, so it's a symmetric detector for now. The material budget is 0.3% x/x0 for inner layers and disks, and 0.8 x/x0, 0.8%, sorry, x/x0 for the outer layers. The beam pipe is made of beryllium with a radius of 18 millimeters in the central region, and then aluminium and a slightly larger radius further out. Now, we want the innermost barrel layer placed as close as possible to the beam pipe, and the innermost disk placed as close as possible to the inner barrel layers. Now, I will show this more on the next slide, but they're actually inside the outer barrel layers. It's here. The default pixel size used is 20 by 20 micrometers, and the default magnetic field is a 1.5 Tesla field, which is the same as the existing Babar solenoid magnet. And the TPC parameterization used is conservative. So, as an example of a study, we have some simulations of disks here. We studied 2 different configurations with either 7 or 5 disks per side. The first disk, as I mentioned, is inside the outer barrel layers, and this arrow points to it. And then the remaining disks are placed outside, first one as close as possible to the outer barrel layers, and then equidistant out to 1.2 meters. So the study I'll present here is the impact of the pixel size and the magnetic field on the resolutions. The parameters used here are they're in the forward region, the studies, which is the pseudoperiod of 3 in this case, just along this line. Single electrons are used from the center, and magnetic fields are uniform 1.5 Tesla or 3 Tesla. So 1.5 I mentioned, the Babar solenoid. 3 Tesla is suggested in the EIC white paper, and also used in a JLab detector concept. An example of other disk studies can be found in the report. Now, the results from this study, and the disk pixel sizes are shown here. This is a busy slide, but we'll go through it. First of all, we have relative momentum resolution here to the left, and then transverse pointing resolution to the right. And immediately, so the different colors are different pixel sizes. Immediately we can see that pixel size has a large effect at large momentum. So for the relative momentum resolution, smaller pixel size is obviously better at high momenta. So the blue is the smallest and magenta is the largest. At the smallest momenta, it doesn't matter much in the forward region. And the transverse pointing resolution also improves with smaller pixel size. So this is good. Now, comparing these 2 plots, we compare 1.5 Tesla field to 3 Tesla field. And if you look at the actual numeric values for the
relative momentum resolution, we can see that the 3 Tesla field is basically a factor of 2 better, which is what is expected from theory. So it's nice to see that in the simulations as well. And the pointing resolutions don't change much, which again agrees with theory. Comparing these two plots, we compare 7 disks to 5 disks, and there's not much difference. The 5 disks has slightly better momentum resolution due to having lower material, but it might be beneficial to use 7 disks anyway, because it has better coverage, because some particles will go through the hole in the middle of the disk and so on, and we want to make sure that particles actually hit some sensitive part of the detector. So what we want, in principle, is as little material as possible while keeping the tracking performance, and this is the challenge. Now, another study we made, which is quite important, is comparing the hybrid to all silicon layouts, so whether to have a gas TPC or not. So we tested various all silicon layouts. I'm only showing the optimized layout here, and more are shown in the backup slides and in the report. And the parameters used here are the central and the forward region is the study is done in. So it's marked here, pseudo rapidities between 0 and 2.5. Single electrons again, and a layer thickness of the outer silicon, which is added instead of the gas TPC of 0.8% x over x0, so it's the same as the outer barrel layers. Now this design is made to keep all the parts physically viable, so layers aren't too long and so on. And we have 5 layers here to aid in the track reconstruction rather than just, say, 2 layers. Okay, so the results from this study are shown here. The pointing resolutions don't change much, so I don't show it. We need large disk coverage to keep the resolution at higher pseudo rapidities. Now, this is relative momentum resolution versus momentum. The hybrid concept is shown in blue, so it's this curve. So, and the rest are all silicon, different all silicon layouts. So what we see, which is very interesting, is that all silicon layouts can outperform a hybrid layout at momenta higher than 5 GeV per C. And this is interesting. This shows that an all silicon layout is not a mad idea. Now, something we need to note here is that a gas TPC provides more points for the reconstruction, and it also helps with the PID a bit from the energy loss. And this does not factor into these simulations, so it's important to keep in mind. Now, another thing we looked at is decreasing the outer radius of the detector. So we want to investigate the performance if the outer radius is decreased for both hybrid concepts and all silicon concepts. And this is potentially very interesting for detector complementarity discussion, because, well, if we're having 2 detectors, one might have a slightly different technology, and a more compact tracker can be desired to make room for other detectors like PID or calorimetry. So what we did for this study was take the best performing all silicon layout and decrease the outer radius. And the same was done for the gas TPC. So here, this sketch shows the gas TPC in blue overlaid on the silicon layout. You can see they have the same outer radii, and then we decrease the whole thing. So this study was made in the central region, pseudo rapidities of -1 to 1. And again, single electrons fired from the center. The study was also made in forward regions, and that's available in the report. The results are shown here. We have relative momentum resolution and transverse pointing resolution again. The colors here correspond to radii, so blue is the same radius for both concepts and so on. So the solid line with circular markers indicates an all silicon layout, and the dashed line with square markers indicate hybrid. And what we can see is the slopes are always different, which means that the all silicon layouts relative momentum resolution deteriorates slower with increasing momentum than the silicon plus gas TPC layouts. We can also see that the smaller the radius is, the better the all silicon is compared to the hybrid. So the blue, the silicon is always the same or better, whereas for the purple, which is the largest radius, there is a crossover point where silicon becomes better. And this is very interesting. Again, because if you want a more compact tracker, then all silicon is the way to go. Now, these were some examples of basic performance studies, and now we can move on to physics studies. So, the physics performance simulations, after CD0 and site selection, which was in January of this year, the studies can become a bit more focused because we now know some parameters better, like the beam line, the beam pipe, and the detector space constraints, and also the interaction rate. So we're working on a new layout based on the new beam pipe and the Alice ITS3 technology, which Laura talked about in the last talk, because this will allow for lower material and smaller pixel size, which should improve our resolutions. So detector simulations can be more realistic now, and the study of the impact of the parameters open for discussion still can be checked, like the silicon vertex tracker radius, the magnetic field, whether to have a hybrid or all silicon, and so on. So we're looking at physics performance using realistic events and event reconstruction. First of all, though, we do a benchmark study because we're switching frameworks. So moving into a new simulation framework, we first do our comparative study. So we export the exact same geometry from EIC root into Fun4All, which is the new framework, and generate single particles in the same parameter space, and run the same analysis code on the simulation results. And these are the results. So here we have the relative momentum resolution on the left and transverse pointing resolution on the right. And well, blue matches blue, red matches red, and so on. So the field lines are EIC root and the dashed lines are Fun4All, and they're basically on top of each other everywhere, which is good. It means there's a good agreement between the simulation frameworks, and this gives confidence that both all the new studies are relevant. So let's move on to this new layout. So a key part of these simulations is to develop and test the performance of a new concept based on the ITS3 technology. So the EIC requires a larger beam pipe than what we've studied previously, which means the innermost detector layers have to be shifted up a bit because the beam pipe radius is larger. While doing this, we also add an extra inner layer. This came by after discussions and some simulations, and we concluded that 3 layers are a good idea and not severely detrimental. And this is especially important at higher B field to register low momentum particles. So here is a sketch of the new design. We have 3 inner layers, which are quite tightly spaced as well, and 2 outer layers. With the ITS3 technology, the material budget can be lowered and the pixel size smaller. So the inner layers now have 0.05% x over x0, and the pixel size is 10 by 10 micrometers, which is very small. So let's move on to the physics events. Open charm events are of the main interest for now, and we use Pythia 8 to generate them. So we do that by the process shown in this diagram. We have electron-proton collisions at a few different energies suggested by the physics working group for the yellow report. And we use the photon-gluon fusion process to CC bar, and the CC bar are then allowed to hadronize freely, so we get D zeros and D stars and so on. The figure of merit for now is the D0 reconstructed mass from hadronic decay to a pion-kaon pair, which is shown in this diagram. And the overall goal of these studies is to find the detector kinematic range in x and q squared and the precision of measurements we can do in terms of x and q squared for varying layouts and parameters. So first of all, we did an initial all-silicon outer radius study again. So all silicon with varying outer radii, as I talked about before as well. We assume ideal particle ID for now, and use all pion-kaon pairings to create an invariant mass spectrum, which is an example of that is shown here in this plot, and a fit to it. And what we see is that the centroid value of the D0 mass peak is within errors from the particle data group mass value, which is nice. So this all seems sane and working. And this plot shows the width of this Gaussian peak versus the detector outer radius. And we see that the width decreases as the radius of the detector increases. And this is also very nice to see. And it is a clear improvement in the mass peak resolution as the outer radius increases, which matches the theoretical prediction for improved momentum resolution at higher radius. Now this is an initial study, as I say, but it's a good start. A better momentum resolution means a clearer peak. We also have an initial magnetic field strength study. So all silicon layout is used again with ITS3 based design with a full outer radius. And the magnetic field is varied, 1.5 Tesla or 3 Tesla. Again, as I mentioned, Babar magnet is 1.5 Tesla, and then 3 Tesla is being discussed. And here are some results. This is for a 1.5 Tesla field, and this is for a 3 Tesla field. And it's quite clear that the 3 Tesla peak is narrower. It also has a higher significance, but that's not shown here. So these are the initial results. So using 3 Tesla improves the mass resolution, this particular collision energy of 29 GeV. But further studies are ongoing for other collision energies as well. Because the risk here is that a higher field causes low momentum particles to spiral before they hit the detector, in which case we lose information. But this study is made with ITS-3-like and 3 inner layers to mitigate this risk. Now this will be compared to ITS-2-like to quantify the improvement we get from going to ITS-3-like. This leads me on to the future work section. Again, the overall goal is to find the detector kinematic range in terms of x and q squared, and the precision of measurements in terms of x and q squared. And we want to optimize the layout and the parameters using these physics events. Now the technical steps to get there are, well, initially at least these. And to further investigate the impact of the magnetic field, as I mentioned in the last slide, and quantify how the ITS-3 design can help us there. We also want to use actual vertex reconstruction rather than simple distance or closest approach. This is more realistic and will show the impact of the pixel size better. We also want to integrate the silicon vertex tracker with other sub-detectors to evaluate the full detector performance. Now, initial studies indicate a discrepancy in the gas TPC performance compared to previous studies, but investigation is ongoing here. And this leads on to the conclusions we have so far. So, we found a few concepts with high performance, both in silicon plus gas TPC hybrids and all silicon configurations. What they have in common is that we need high granularity detectors and low material close to the interaction point. Further out, we can relax the material budget a bit, but it's of course better to keep it as low as possible everywhere. The pixel size needs to be kept small. The current baseline of 20 by 20 micrometers performs well, but we are now investigating improvements we can gain from the ITS-3 technology, which would be 10 by 10 micrometers. All silicon layouts can match silicon plus gas TPC hybrid layouts above a few GeV per C, and it actually outperforms them at higher momenta. And a key point is that if a smaller radius detector is desired, it's better to replace the gas TPC with silicon layers. Simulations of physics performance are ongoing. We're evaluating the proposed ITS-3-based concept and want to assess the improvements it brings. And initial results are promising, and also the simulation framework yields credible results, which is very good. And that concludes this presentation. Thank you.
Hello again, and that's that talk. So I hope you enjoyed it. It went well when I gave it, I think, and I got some questions and some nice ideas about future work and what more to show, which was good. So yeah, let me know if you have any questions, comments, and so on down in the comments, and I'll see you next time for probably a gaming thing. I'm going on vacation now, but I'll see you around hopefully soon enough, yeah? Okay, bye!